So we can combine these three simple gas laws into a single gas law. If you're interested in the math, ask me and I'll show you. What we end up with is what's known as the ideal gas law. PV equals nRT, sometimes referred to as PIV-NERT. So here we have pressure, volume, amount of gas in moles, and the temperature, and then we have one extra letter in here, and that's R. R is a constant to make this equal instead of just a proportionality. So the ideal gas constant, R, is equal to 0.0821, and it's got really weird looking units. Liters times atmospheres divided by moles times Kelvin. The ideal gas constant is a constant, and so it's always the same number. With this gas law, we have to be more careful with what the units are. In the other gas laws, the only one that we cared about was the temperature had to be in kelvins. The other quantities, as long as they were the same unit, it was fine. Here, we have to use particular units. The pressure has to be in atmospheres. The volume has to be in liters. The amount of gas has to be in moles. And as always, temperature has to be in kelvins. This is a table that summarizes the relationships, and there's also another one, Gay-Lussac's law, that relates pressure and temperature. Let's do an ideal gas law problem. Now, one of the issues that students have when dealing with these problems, you get them on an exam, they're all scrambled up. They don't have these convenient little titles that tell you what they're about. So how do you know which law to use? Well, it's not always obvious. But you can always take the approach of make a table, collect and identify the numbers. And then the table will help you decide what equation you need to use. So we know this is going to use the ideal gas law, but we're going to pretend that we didn't read the title, okay? So we read the problem, calculate the volume occupied by 0.845 moles of nitrogen gas, a pressure of 1.37 atmospheres, and a temperature of 315 Kelvin. Okay, so we draw the table, and we start collecting the numbers. So the first number is 0.845 moles. 0.845 moles. That's the amount of gas in moles, and so that's N. Next one is 1.37 atmospheres. 1.37 atmospheres. So that's the pressure. That's great. Temperature of 315. Well, this is looking a little different now, right? We don't have another N or another P. We have to extend this out, 315 Kelvin. And we came to the period. Okay, so this is the temperature. There's only one row. So we can't use one of the gas laws that has ones and twos in it because there's only one set of conditions. The table was not a waste of time, though. It has organized our numbers for us. So I'm just going to erase the extra stuff here that we didn't actually need. And there we have everything nicely arranged for us. So we're going to use the ideal gas law, PV equals nRT. PV equals nRT. So what are we looking for here? We're looking for the volume. It says calculate the volume. We can also look at this and say, well, what don't we have up here? Well, we don't have V and we don't have R, but R is always the same. R is equal to 0.0821 liters times atmospheres divided by moles times Kelvin. I will give that to you on the exam. So we're looking for V. The nice thing about the ideal gas law, no fractions. So we'll rearrange it to find out what V is by itself, dividing both sides by P. So the volume equals N times R times T divided by P. So we put all these in. So N is 0.845 moles. And R, we wrote down up there, 0.0821 liters times atmospheres divided by moles times Kelvin. Yes, I know it's tedious. And the temperature, 315 Kelvin. And that whole long thing divided by the pressure, 1.37 atmospheres. I wrote all the stinking units. Let's look at the units and make sure that they're working out okay. So I have atmospheres up here and atmospheres down there, so those are going to cancel out. This is a little complicated because I have a fraction within a fraction. I have a Kelvin here and a Kelvin there. Those cancel out. I have mole, and those cancel out. If one of my quantities was in the wrong unit, maybe volume was in milliliters, then the units wouldn't cancel out. And I'd say, oh, wait a minute, I need to fix something. You can also head problems like that off by just looking at the units on the ideal gas constant. Those are the units that the other quantities have to be in. They need to be that so the units work out. So we've got our units doing okay. 0.845 times 0.0821 times 315 divided by 1.37. Looking at all of those numbers, they all have three significant figures, right? The ideal gas constant is not an exact number. So we end up here with volume equals, my calculator's giving me a big mess. So I identified the number of significant figures, so I write those down. I write down two extra ones. The unit is liters. And now I can see that I need to round this. The 5 makes the 9 round up. And so I'm going to end up with 16.0 liters. I wanted three significant figures. My answer here has three significant figures. That 0 is important. Any questions? This is a very straightforward ideal gas law problem. You can't really look at this and say, does it make sense? Because that's really hard to judge. Oh, here's another one. An 8.5 liter tire is filled with 0.55 moles of a gas at a temperature of 306 Kelvin. What's the pressure of the gas in the tire? So maybe we've done some problems now and we've got a better idea of what's going on, and we look at this and we think, nothing's changing here, right? We're not saying that it got colder or that we added stuff or anything. So this is probably just an ideal gas law problem. So you can make the table or you can just label the numbers. So I'll try that for this problem. So 8.5 liters. What is that? That's a volume. The unit tells us that, if nothing else. 0.55 moles of gas. That's N. And 306 Kelvin. Whoops, that's the temperature. T. What's the pressure, it says? Well, pressure equals question mark. We don't know. So write down the ideal gas law, PV equals nRT. We want to find the pressure. So this time we're going to divide both sides by volume. Pressure is equal to nRT over V. Okay. What's R? Well, after you do a few problems, you might remember what R is, but otherwise go look it up and write it down here with its units. 0.0821 liters times atmospheres divided by moles times Kelvin. So this is equal to 0.55 moles times R, 0.0821 liters times atmospheres divided by moles times Kelvin. And yeah, it's tedious to write that out, but it's tedious to repeat the class also. Temperature is 306 Kelvin divided by the volume, 8.5 liters. So pressure equals, we'll do the math, 0.55 times 0.0821 times 306 divided by 8.5 equals. This time, two of my numbers had two significant figures and two of them had three. So my final answer is going to have two significant figures, 1.6, the next two digits are 2.5. The unit, so my moles canceled, the liters canceled, the kelvins canceled, and so my unit left is atmospheres. And that rounds to 1.6 atmospheres. Oops. Okay. How much volume does 0.556 moles of gas occupy when its pressure is 715 millimeters of mercury and its temperature is 58 degrees Celsius? So I look at this and it's like, well, I've got moles and pressure and temperature, and I only have one of each. This is probably going to be an ideal gas law problem. So I'm just going to identify these things. So I have 0.556 moles of gas. Well, that's N. And pressure is 715 millimeters of mercury. That's the pressure. And the temperature is 58 degrees Celsius. And R is our old friend, 0.0821 liters times atmospheres divided by moles times Kelvin. So PV equals nRT. And solving for V, so we divide by P on both sides. Volume equals nRT over P. Now, two things could happen here. You could just plug those numbers in, and if you wrote your units in, like I'm telling you you need to, you will notice that they don't cancel out, right? Or you may look at this and say, oh, those aren't quite the right units. I'm looking at the units in this, and those are the units I need in my other numbers. Moles is fine, but millimeters of mercury isn't going to work. Degrees Celsius isn't going to work. So I'm going to convert those before I stick them in there so I don't have to erase a bunch of stuff. The third option is you plug all the numbers in without thinking about the units, and you do a very nice calculation and you come up with the wrong number. I don't recommend that one. So converting millimeters of mercury, we need to convert to atmospheres. And these pressure conversions can always be done in one step. We put this unit we want on the top and the unit that we're starting with on the bottom. This is one that gets used a lot, so it'll save you some time if you memorize it, but it will be in the table provided for you. 1 atmosphere is exactly equal to 760 millimeters of mercury. So 715 divided by 760, 0.940. 715 has three significant figures. We want to keep a couple of extra digits here so we avoid rounding errors. So there's my three significant figures, and I'm going to keep the next two digits, 7, 8, and now the unit's atmosphere. The temperature was given in Celsius. We need to convert that to Kelvin. by adding 273. So 58 plus 273 is 331 Kelvin. For temperatures, it's an adding operation, and so the rules for sig figs are different. It has to do with numbers of decimal places. But the shortest and best method for temperatures is to look at what digit is the uncertain digit. Here it's the ones place. After I convert this temperature, my uncertain digit should still be in the ones place. And here it is in the ones place. So yes, I gained a significant figure. That can happen. Don't be alarmed. Okay, so now we've got the right units. Volume equals. And sometimes you'll be given a problem where the amount of gas is given to you in grams, and then you have to convert to moles. They didn't do that to us here. 0.556 moles times R, 0.0821 liters times atmospheres divided by moles times Kelvin. Times the temperature, 331 Kelvin, divided by the pressure, 0.94078 atmospheres. All my units are working out like I had hoped. I underlined this third digit here because that's the uncertain digit, and that reminds myself that this number has 3 significant figures. When I look at this whole thing, I see 3 sig figs, 3, 3, and 3. My answer should have 3. So I do the math, 0.556 times 0.0821 times 331 divided by 0.94078. And I'm thinking 3 significant figures. That saves me from writing down all the garbage my calculator gave me. 16.0, there's 3 sig figs. Next 2 digits, 60. The unit that isn't crossed out is liters. Then I round, 16.1 liters is the volume. Any questions? We can use the ideal gas law to experimentally determine the molar mass of a gas. This is something that's a little challenging to do with liquids and solids. So what we can do is we can measure the mass of a gas and its volume at a given temperature and pressure. And using the ideal gas law, we can find out how many moles of gas is in that mass. Remember that molar mass is equal to the mass in grams divided by the amount in moles. So that's what we need. We need the grams, the mass in grams, and we need to know how many moles of gas are in this sample. Well, we're given the mass in milligrams, so we could convert that to grams, 38.8 milligrams. We want grams. Milligram has a prefix, gram doesn't, so we have a metric conversion with 1 prefix, so we just do this in 1 step. We've got grams on top and milligrams on the bottom. Then we rack our brains to find out, what does M stand for? Milli stands for 10 to the what? -3. So 10 to the -3. So here's milli. I don't want to put what it means right next to it. I want to put what milli means on the other side of the line. Because up here, instead of writing milligram, I'm going to write what milli means, 10 to the -3. So 1 times 10 to the -3 grams is equal to 1 milligram. The milligram units cancel out. Remember, on your calculator, the way you enter something in scientific notation will be 1 EE -3. There's no times 10 or anything. And so this is going to give me an answer of 0.0388 grams. The next thing I need to do is find out how many moles are there, right? So I've got a volume, I've got a temperature, and I've got a pressure. Are any of them in the correct units? Nope. They are all messed up. So let's work on that. So the volume is 224 milliliters. What unit does that have to have? Liters. So we convert this to liters. So liters on top, milliliters on the bottom. Same thing we just did with grams and milligrams. Milli still means 10 to the minus 3. So we put 10 to the minus 3 here. 1 times 10 to the minus 3 liters is 1 milliliter. So we do the math and it comes out to be 0.224 liters. 55 degrees Celsius is the temperature. So we have to convert that to Kelvin. I should be able to do that in my head, but I don't trust my head. 328. And the pressure is given to us in torr. What does it need to be in? Atmospheres. So we need the relationship between atmospheres and torr. Torr is a different name for a millimeter of mercury. 1 atmosphere is 760 torr. So the torrs cancel out. We have 886 divided by 760. 886 is 3 sig figs, and this relationship is exact, so my converted pressure should have 3 significant figures, but again, I want to avoid rounding, and so I'm going to write down 2 extra digits. If you're going to make a mistake on significant figures, make the mistake of putting too many. It's very easy to get rid of extra ones later. If you write down too few, you have to do the math all over again to get them back. And I've got volume, temperature, and pressure in the correct units. So to find the moles, I need the ideal gas law. PV equals nRT. This time I'm solving for N. So I'm going to divide by R and I'm going to divide by T. Those will cancel out. I have to do the same thing to both sides. So N is equal to the pressure, 1.1657 atmospheres, times the volume, 0.224 liters, the whole quantity divided by R, 0.0821 liters times atmospheres, divided by moles times Kelvin. And the other thing in the denominator there is the temperature, 328 Kelvin. The units are canceling out nicely. What I end up with there is 1 over mole. So mole does a somersault and ends up being in the numerator. This one, we have 2 numbers in the denominator, so on your calculator you need to be careful. Students tend to want to multiply these 2, and if you're going to do that, you got to use parentheses. So that would look like 1.1657 times 0.224 divided by, parentheses, 0.0821 times 328, parentheses, equals. If you leave the parentheses out, you're going to come up with a different answer that is not going to be correct. How many significant figures should this result have? 3. All of these numbers happen to have 3 significant figures. So I'm going to write down the first 3 significant figures. Those leading zeros don't count. Common mistake. So 9 is the first one that counts, 6, 9. And then I'm going to write down 2 extras, 6, 5. And the unit there is moles. This is not a final answer, so I don't want to round this off yet. We don't really have enough space here, so I'm going to make a little space so we can continue. So I have the amount in moles and I have the amount in grams. This problem is longer than some of the ones we've done. And sometimes you forget what you were trying to do in the first place. So you have to go back and think about it again. I'm trying to find the molar mass. I need the mass in grams and the amount in moles, and then I'm going to divide them. So the molar mass is the mass in grams divided by the moles. So I found both of those numbers. I've got 0.0388 grams, and I divide by the amount in moles. Yes, it's a little tiny number. It's okay. At 0.0388 divided by 0.0096965. And this result should also have 3 significant figures, 4.00. Write down the next 2 just to be safe. And then you can round it, 4.00 grams per mole. And that is our answer up there. Is that a reasonable molar mass? Is it a possible molar mass? Could there be something that has a molar mass of 4? Yeah. Helium. Helium's actually the only thing that has a molar mass of 4. What if I ended up with a molar mass of 0.5 grams per mole? Is that possible? What's the smallest element? What's its molar mass? 1. And hydrogen doesn't hang out as atoms, it hangs out as molecules with a molar mass of 2. So if you end up with a molar mass that's less than 2, something went wrong. Any questions? Pretty much guarantee that there'll be a problem that asks you to calculate the molar mass on the next exam. This kind of problem is a little tricky, so we'll do another one. Sample of gas has a mass of 827 milligrams. Its volume is 0.270 liters at a temperature of 88 degrees Celsius and a pressure of 976 millimeters of mercury. Find its molar mass. So we'll take the approach of write down the numbers, right? Label the numbers. So 827 milligrams is what? Not volume. It's a mass, right? So mass is M. The next number is 0.270 liters. That's our volume. Volume is, next one says temperature of 88 degrees Celsius and pressure of 976 millimeters of mercury. Those are all the numbers I was given. Find its molar mass. Well, we've been doing a lot of stuff with the ideal gas law, but does the ideal gas law have molar mass in it? No. but it allows us to calculate the moles. And let's think, I'm just going to go ahead and make space up here to start with. Let's ask ourselves, well, what is the molar mass? What are the units of a molar mass? Molar mass has units of grams divided by moles. So to find the molar mass, I need to find how many grams is this sample and how many moles is the sample. Well, I've got a mass up here, but it's in milligrams. So I'll need to convert that to grams because the unit up here is grams. So milligrams on the bottom, grams on top. Milli means 10 to the minus 3. Millis on the bottom, I put the 10 to the minus 3 where the milli is not. The milligrams are going to cancel out. And you do that on your calculator, you're going to come up with 0.827 grams. So that goes up here, 0.827 grams. Now I need to find out how many moles. Well, moles is N in the ideal gas law. So I've got a volume, I've got a temperature, and a pressure. I know what R is. R is 0.0821 liter atmospheres per mole Kelvin. I need the ideal gas law. PV equals nRT. Rearrange that to get N by itself. So N is equal to PV over RT. In the ideal gas law, the units are very important. I need the units that are given in the ideal gas constant. So my volume is good. Liters is the unit of volume here. My temperature is in Celsius, so that's not going to cut it. So I need to convert that to Kelvin. 273 plus 88, 361. This pressure is in millimeters of mercury. I need atmospheres. So millimeters of mercury on the bottom, atmospheres on the top. 1 atmosphere is 760 millimeters of mercury. 976 divided by 760. My pressure had 3 significant figures. I need to keep 3 and 2 extras to avoid rounding errors. And so there's my pressure in atmospheres. And now I've got all the pieces I need. I can put them in here. Pressure, 1.28. 42 atmospheres. Volume, 0.270 liters. R, 0.0821 liter atmospheres per mole Kelvin. Temperature, 361 Kelvin. I check the units. Moles are down there. Atmospheres cancel, liters cancel, kelvins cancel. There are a lot of little steps in these problems, aren't there? And it's really easy to make a mistake. That's why it's very important to learn how to write everything down clearly so that you can read what you've written, okay? I know some of you are challenged in the handwriting department. Do your best. If you can write things out clearly, then if your mind wanders, because maybe you think about squirrels, you can come back and you can see what you were doing. It's actually a skill that helps you learn how to think better. Okay, so it's good for passing Chem 3A, but learning how to put your thoughts down coherently on a piece of paper will help you with all sorts of things later in life as well. So I've got everything written down here. You know, I got talking to you guys and I forgot what I was doing, and so I can look and, oh, I didn't finish this part, so I need to do this calculation, and that's what I'm going to put up there. And if you find, in spite of writing stuff down like this, that you still get lost, write yourself a short set of instructions before you start doing all of this so that you can go back to that if you get lost. 1.2842 times, that's the wrong button, times 0.27 divided by 0.0821. Oh wait, that's not what I was doing with you. There's different ways to do this. So here we have that situation again where we're dividing by two numbers. So what most of you will want to do is multiply. So you can do that, but put parentheses around it. So I've got the times 0.27 divided by, I'm going to open parentheses, 0.0821 times 361, close the parentheses. And then my calculator is giving me a whole bunch of numbers. I'm looking at the numbers that I have, and I'm seeing that 3 is the smallest number of significant figures. So this result needs to have 3. Leading 0 doesn't count. 1, 1, 6. There's my third significant figure. Write down 2 extras. And the unit is moles. That's what I need for my molar mass calculation up here. I need the amount in moles. So 0.011698 moles. 0.827 divided by 0.011698. This result is also going to end up with 3 significant figures. There's 3. Write down 2 extras. Now I can round that. I see that it's going to be 70.7 grams per mole. That's more than 2, and it's not ginormous. If you end up with, 70 billion, that's probably wrong as well. So that seems like it would be a reasonable molar mass. Any questions? When you type all of these numbers into your calculator, it's really easy to press one button wrong. And that's all it takes to get the wrong answer. So what I really recommend doing, punch all the numbers through, write the answer down, clear your calculator, go back and do it again, and hopefully you'll come up with the same number. If you get a different number, write that one down also. Clear your calculator, do it again, go for best 2 out of 3. Those errors you're making are random, and so you're very unlikely to make the same mistake twice. On an exam, you've gone through everything and you're wanting to go back and check your work. Well, go back and everything's written down here. Go back and check your math. Make sure that those calculations are correct. You can do that because you wrote everything down. The behavior of a gas depends on the conditions. So we've talked about the ideal gas law, and that describes the behavior of an ideal gas. Well, no gas is truly ideal, but under certain conditions, gases behave in an ideal way. And these are conditions of high temperature and low pressure. This is good for ideal behavior because we have the particles being very small compared to the space between them. And we have the interactions between the particles being insignificant. So these particles are going to collide with each other, and when they do, they're moving fast enough that they really have no time to interact. It's like people in New York City rushing to catch a subway or something, and you bump into someone, and you don't even notice if they're hot or not. You just keep going, right? You have to catch the train. But if you're in a very slow-moving place, like these conditions of low temperature means that the particles are moving more slowly. Maybe you're just strolling through the park and you bump into this guy and you notice, wow, he's really hot. And then maybe you start talking or something, right? Because there was enough time there for you to have an interaction. When the gas particles are moving fast, there's no time for an interaction. When the gas particles are moving slowly, there is some attraction between them, and that does not follow the kinetic molecular theory where there's no interaction between the particles. So what happens when we have high pressure and low temperature is now because of the high pressure, there's not nearly as much space between the particles. Now the volume of the particle itself becomes significant, and there are interactions because the particles are moving very slowly. Have you ever been to Wyoming? The entire population of the state of Wyoming, which is not a small state, it's not like Rhode Island or something, it's about the population of Fresno without Clovis. The whole state, right? So think about the state of Wyoming, less than 500,000 people in the whole state, and now think about an elevator with 10 people in it. Okay? In the state of Wyoming, does it matter if all of the people are giants or little tiny slips of people, little 98-pound weaklings? There is so much space in the state, it doesn't matter at all. Does it matter on the elevator? Yeah. If you've got 10 kindergartners or 10 Fresno City linemen in the elevator, you're going to notice a big difference, right? The size of the people, because they're so close together, becomes significant. That's what happens with gases under high pressure. They're squeezed together. Kinetic molecular theory says that the size of the particle is so small relative to the size of the gas that it doesn't matter at all. But when you squish them together, it starts to matter. So when you have low temperatures, high pressures, they do not obey the ideal gas law.